So again, if you're just joining us, you can type in your questions in the Q&A panel. We'll answer them along the way, and I'll answer any at the end that we don't get to. And then for a best view, so you can see different parts, like this awesome copper heat exchanger, you can control the side-by-side view to see which part of the slides and the camera, how big each one is. All right, let's get started. So, today's webinar is on additive manufacturing for the electronics sector. And while a bunch of the examples are from the consumer electronics, it's really beyond that. There's a lot of commonalities between just products that involve electronics. And so I'm going to slightly expand it a little bit beyond just consumer electronics. I'll talk a little bit about additive manufacturing 2.0, what's new in this ability to make mass production a reality, and how and why it's a game changer for the electronics field. Talk a little bit about the metal binder jetting, how it works, what you can expect, the kind of constraints, capabilities of the process, and then we'll spend most of the time on a whole bunch of application examples, many of which are within about 1.5 feet of me, so I can reach them and show them to you. And then we'll take your questions and cover just a bit on finishing methods, because that's one of the questions folks have in the consumer electronics space. So first, just for a little context, our mission at Desktop Metal is to make industrial grade 3D printing accessible to all. So that's engineers and designers, so early part of the manufacturing process, but also manufacturers, and that's really what's new. People have been able to make prototypes for some time, but this idea that you can now replace a lot of conventional manufacturing processes like casting, metal injection molding, machining, stamping, etc., with additive manufacturing is a game changer. So we'll talk a little bit about that. And quite simply, our promise is to provide cost-effective, high-speed printing systems that give you exceptional quality parts. We're now in our 4th year of shipping product. Hundreds of brands around the world are using us and printing on our systems as we speak. And you'll recognize some logos here, but many you won't. And that's kind of the point, that metal additive manufacturing is now a reality for small, medium businesses, as well as the global giant companies. And so they're accessible, they're affordable. And so now you see small, medium businesses, which is really in many ways the backbone of manufacturing, start to use this technology as well. There's a full range of solutions from Desktop Metal, everything from super accessible, easy to use studio systems. You can print and sinter 2 steps right in your office, right next to your desk. We and our customers are doing that every day. And then there's a shop system and the production system for kind of to go from pilot, from batch runs, pilot runs, all the way up to mass production. And mass production might be millions or more parts per year. So really the full scale from 1, 2, or 5 parts per day to 100, 1,000, and even thousands. So why is additive manufacturing really of interest to the electronics space? Well, there's a bunch of important constraints that we as engineers and manufacturers have lived with. There's constraints on the geometry. You kind of have to think about, well, design for manufacturing. What are the constraints of whether it's stamping or machining? There's limitations with respect to customization because of tooling costs. And then if you think about the process, there's an opportunity for process innovation. Time to market pressure today can easily take months to stand up a new production line, and tooling is a giant part of that. Volumes, with tooling being a giant fixed cost, you want to amortize it over large runs, and so really you got to order a lot. There's long lead time, so you kind of have to guess what will be in demand, what the demand might be like several seasons from now. Inventory is a challenge. If you think about the production rates and you're making a part today that might make it to the consumer 9 months from now, so somebody is warehousing those parts. And then just the part cost, the economics. So all of those are addressed via additive manufacturing, and we'll see a bunch of examples of that. Everything from the geometry, you now have a lot more freedom to optimize design, to incorporate moving parts in a design. You can really do things you couldn't before. A lot of opportunities for customization, whether that's making a whole bunch of parts, each one a little bit different, or local factories where you're printing just for that part of the world. Time to market, I mean, we'll go over the specifics, but it's literally shaves 80–90% off the time where you can start to produce parts and get them into customers' hands. Volume, you can print 10 and you can print 100, or you can print 1,000 next week. So really, without tooling costs, you have tremendous flexibility with respect to production rates. And so you can, whereas in the old days, or I guess today's reality for many of us, you ship parts via land, air, and sea. You now can just ship files, and that file is getting printed today in every part of the world that has an additive manufacturing printing system. And we'll see some of the examples, but the costs, not only can you have all these business flexibility aspects, and the geometry can change, but the cost is not just on par. You can actually save a lot of money, both on the part costs, but also the downstream costs, the finishing, post-processing, that kind of thing. So let's talk a little bit about what enables this notion of tooling-free manufacturing. You think about traditional manufacturing processes, and really these are machining, stamping, progressive dies, could be forging, casting, powder metallurgy. The challenge is to set up one of these production lines. They're great for once you're starting to mass produce parts, if you need to make not so many different kinds of parts, but there is long lead time to stand up the lines. There's large non-recurring engineering costs in making this tooling, and the processes are quite industrial, and there's a fair bit of waste. There's also, whether it's custom machining, quite often, even with phones that might be forged, there's a lot of machining that happens afterwards to really then assemble it. So there's a lot of processes, and the result is it takes months to stand up a production line. There's not a ton of opportunities for design iteration or customization, and you need these large quantities. Large quantities is fine once the product is verified, tested in the market, pilot runs, but there's often you want to ramp up. So there's kind of a bridge to mass production that today there isn't a great alternative for. And additive can not only fill that, but also take a lot of the mass production as well. So let's talk a little bit about the specifics about three popular ways. I don't have progressive dies on here, but they're not dramatically different, the story. If you're going to do machining, there's preparation, and then there's iteration. It really takes, if you're going to be making thousands, tens of thousands, or hundreds of thousands, maybe millions of parts, there's probably something on the order of a couple of months for a well set up CNC operation to start cranking out this new design. It's not quite as simple as you take the 3D model, you run the CAM program, and you start spitting out the parts. So there's a bunch of these steps with the tooling, the work holding, soft jaws, trial, error. There's consumables, every so often the cutters wear out. So all of that, there's easily both kind of months to set things up, and as well as consumable costs that are not trivial. They're actually a large part of the cost structure. Then castings, if you think about castings, it takes really 4 months. 4 months is quite typical. We've seen 3 months, we've seen 6 months, 7 months to set up both the prep in terms of mold design, iteration on the molds, and then the production itself, whether it's wax parts, the slurry coating, trying all of these things. And with MIM, it's another even longer process. So MIM, and we'll talk specifically about MIM because that actually has a lot of connection to binder jetting and metal additive manufacturing. But it takes months to produce the tooling, to verify all the stuff. And then think about what happens if the design changes. If the design changes, a lot of the tooling costs, the know-how, the process development, time motion studies, etc., goes out the window. You kind of have to start over. There's some potentially, if it's a relatively minor design change, you can use a lot of both the know-how and the setups, but it's not guaranteed. And that's why this whole thing, a lot of these processes are great once you've established something and you want to make it for years, but it's not as effective when things change, designs change, tastes change, models change. So with binder jetting, all of these steps, there's still prep, there's still pilot production, there's still tuning, there's a bunch of knobs to turn, there's a post-processing to be worked out, but all of that together, it's routinely, we're seeing, our customers are seeing 1 or 2 weeks. So they're delivering parts instead of literally companies that were delivering MIM parts 3, 4, 5 months later, today are delivering parts to their customers via binder jetting, via our binder jetting solution in just a short number of days. And by the way, if the design changes with binder jetting, you can print a new design within the same build as you're printing the old one. So there's absolutely, this is the whole point. As long as you have the 3D model, you can update, everything updates, and you can start printing today. So the reason this is a really exciting time for the electronics sector is additive manufacturing is at an inflection point. If you think about it, over the last 30, maybe even 35 years, there's been 3D printing's been around. Even metal 3D printing, laser powder bed fusion has been around for 30 years or so, but it's just too industrial, too slow, and too expensive to be viable mass production processes. And that is what's changing. That's what's exciting. So additive manufacturing is around the corner. It's actually here, and we're one of the players making this possible. And that's simply the ability to repeatably, in high volume and cost competitive price points, have parts that are great in terms of finish and accuracy, property, etc. So there's kind of 2 things that are making this possible. One is the accessibility of printing systems. Accessibility in terms of costs, as well as accessibility in terms of ease of use. These are systems designed where, for example, the desktop metal shop system, you bring it into your shop, and your crew that today might be machining or post-processing or finishing parts can start printing. And the speeds are such that high volume manufacturing is actually possible. So the promise of Additive 2.0, our promise to you, is that you can print parts where the finish, the accuracy, material properties, and the cost and speed are such that it is a game changer for electronic components. So there's a lot of opportunities for in electronics. Today I'll cover just a few of them, because it's actually, I literally ran out of a few slides to put all the different examples on. But I'll show a few of these, and they fall into broadly these categories of, you got enclosures. So for example, whether it's wearables, so this is kind of an over-designed but nice example of a part you can create. You can do, certainly can do, phone enclosures. So these were, when they were simpler and they were stamped quite often out of aluminum. But as the phones get bigger, as we put them in our back pocket, and as we get bigger, so that when we put them in the back pocket and sit on them, they flex, they got to be stiffer. And so suddenly now you need stiffer, but you don't want to have the phone be too heavy. And so believe it or not, what used to be simply stamped are now machined, even sometimes forged, but all of that requires setup tooling. There's actually factories in parts of the world where there's 10,000 CNC machines in one place, just spending 20, 30 minutes machining out enclosures for consumer goods like smartphones. There's mechanical components and systems. So for example, here's a complex little sensor holder. This part normally might be metal injection molded, but now you can 3D print it. You can 3D print it at scale, and when the design changes, you just start printing that same day. Latches, fans, you can do whole transmission systems. So for example, here's a part, gear system. I'll show some more examples of that. So really, thermal management. So whether it's heat sinks, for electronics, custom heat sinks, bus bars. I'll show you the inside of this part. Actually, it gets hot, so there's literally a cooling channel running to dissipate the heat. There's electrical components, whether it's antenna, fans, or stator, motor stators, and of course the old friend manufacturing tooling. That's been around for a long time, but I'd be remiss if I didn't mention that 3D printing is making it possible, both in terms of polymers 3D printing as well as metal 3D printing, manufacturing tooling, jigs and fixtures, end of arm tooling. All of that can be and is being used on the manufacturing floor for electronics. So before jumping into a few of the cool examples, application examples, I wanted to show a little bit about how does this stuff actually work. So what we've built at Desktop Metal are printing systems. The entire family you saw of the metal printing systems, they're built around the chemistry and the powder supply chain of metal injection molding. So what does this mean? Well, metal injection molding is a mature, well understood powder metallurgy process, and that allows for really complex parts to be mass produced from relatively inexpensive metal powders. This is a mature technology. It's widely accepted, validated. There's international standards for how to characterize these materials. And this is an approach that allows a very broad range of alloys. There's over 100 different alloys that are compatible with MIM. So what's the point? The point is MIM is a great way, is a great foundation for printing a very broad range of components for the electrical electronics manufacturing sector. How does it work? So how does MIM work before we jump into what have we done to build on top of MIM? Generally, metal injection molding, you have metal powder that's mixed with a polymer binder to create the feedstock. That feedstock, the next step is to create the shape out of this feedstock. And that step is injection molding, very similar to plastic injection molding. That creates the shape. So there's tooling that gets created, and this feedstock is heated and under pressure injected into the molds. Now, it's heated to just a couple hundred degrees Celsius, so that what melts, of course, is the polymer binder. The metal powder doesn't melt, but the metal powder comes along for the ride. And so now you have the shape that you've created using the mold. There's a solvent debinding step to take out some of the solvent, and then there's a sintering step, which makes all of the remaining binder evaporate, and through solid state diffusion bonding, the metal particles come together. And you have the metal part. Well, with binder jetting is and let's see if I can play the video while I'm talking. Binder jetting is an additive manufacturing powder metallurgy process where layer by layer, so instead of having molds and inject this feedstock into the molds, instead a layer of powder is put down, and selectively, through a very high-speed process, the binder selectively, just like with inkjet printing, this is essentially a 3D printing press. We're just printing one layer at a time. So the binder is selectively deposited onto the powder bed, and that binder acts as a temporary glue. The temporary glue is what defines layer by layer the shape. And then, why is this a game changer and a key technology for mass production? Well, you can create a lot of parts very quickly. You can print a giant build box in just a few hours. And so this is very high throughput instead of, with, for example, laser powder bed fusion, you draw with a laser very much slower, like 50 or 100 times slower. And so it's laser powder bed fusion is a great way to make a few parts, but those parts are expensive and really they don't lend themselves to mass production. With binder jetting, you now can use this low-cost material input that uses the supply chain and economics of an established metal injection molding industry. And but now you have the flexibility because you don't need the tooling that you do with metal injection molding, you can now create the geometry you want. So it winds up with attractive part costs, and you get great material properties. And this is scalable from modest size build boxes all the way to large build boxes and large parts. Most of the parts I'm showing today are relatively small, but we've printed parts, and customers have printed parts that's literally the size of the build box. It's not yet recommended to do that en masse, but I've seen that done. And this actually, as a process, is a much lower waste process. The materials are entirely reusable. So whatever you depowder, you actually can reuse again. And so the key steps in the process are, there's a print step. So there's a printer that layer by layer spreads the powder, precisely jets the binder to create this sand castle, except it's not sand, it's metal powder particles that are later sintered. Then once the build box is complete, you then depowder it. And it's done in order to separate the part that you defined with the binder from the rest of the powder. So that's separated. And then those parts go into the furnace for sintering. There's a couple different systems to note. There's the shop system, which is really great for batch production of dense, fully dense, ready parts. And it's really optimized for the kind of volumes and the kinds of parts that are made in the machine shop. It's a scalable solution. There's 4, 8, 12, 16 liter systems. And you can make, I'll show a bunch of these parts, and you can make literally dozens or hundreds of parts per day without tooling. And the parts change, design changes, start printing them in the second build of the day. And all the way up to there's the production system. The production system is if you want to make this. I mean, this is a big boy. If you're making lots and lots of parts, what's lots? Many thousands or hundreds of thousands or even millions of parts per year. You're making consumer products, then the production system. It has favorable economics over all the other systems both out there, and even and it's the most efficient way to produce parts, but the volumes have to justify it. So this is kind of the trade-off. You want to start printing with a shop system tomorrow for one kind of range of price points and volumes, or if you want to make mass production kind of parts with dramatic cost benefits. So now let's talk a little bit about the application examples. I'll show a few of them briefly. So could be watches. And by the way, for every part I'm showing you, there is, to some extent, sadly, at least for us, a lot of our both prospects and customers that are evaluating or using these systems, of course, the products, these are the early days of binder jetting for consumer electronics. And so for every part you're seeing, there's about 10 applications that are not yet public case studies. And that's understandable. Every organization wants a competitive advantage. So they want to come out with these products first, and then we'll do some case studies. Anyway, so I can't show you everything, and we can't name some of the customers, but basically there's enclosures, there's thermal management solution like heat exchangers, depending on what's going on. For Cube satellite, there's antenna feed horn, so maybe smaller or mid-sized volumes, complex geometry, start printing it today. Motor stator, sensor holders, electromechanical components, closure latch, the parts. There could be fluids depending on what else is going on inside the electronic component, and so there may be parts that you would otherwise cast. Heat sinks. There's support brackets, so you can do things. Normally you might cast the part. Maybe you want the consumer electronics component to be relatively light, but there's a need for a bracket or brackets, and so you can really optimize the geometry, remove material where it's not needed, and not worry about either tooling costs or having excess weight or material. So let's just jump into a few of these categories. So one, enclosure. Here's an enclosure for a wearable device. In the old days might be last year or a couple of years ago, it might be this part might have been plastic injection molded or aluminum. However, what folks have discovered is increasingly, these have to be stainless steel, due to the stiffness, because you're trying to pack more in, and there's just not a lot of room for the enclosure itself. It's got to be stiff. It's got to feel like a premium thing, not too cheap, but also corrosion resistance. Everything from the elements to sweat or sunscreen actually can really impact. And so being able to use stainless steel, being able to finish, and we'll get into plating and other finishing method, is important. And then there's, of course, consumer product. Time to market is key. You want to minimize tooling costs. You want to have flexibility. You want to reduce the inventory turns, kind of make to order. That is all possible. And as an example, with that part, with a production system, you can make over 1,000 per day. And so really 1.5, almost 2 million per year at fairly competitive cost. These parts previously they're too complex for forgings, and so metal injection molding was the primary way, with a ton of post-processing. There's literally factories overseas. The labor doesn't make sense to do it in places like Europe or North America. But you have factories where these parts are MIM'd and then post-processed. And now instead you can make a near net shaped part right in the production system. Smartphone enclosure, I already showed this part. Used to be relatively a straightforward part to stamp out of aluminum. Now people are moving to more exotic materials and more complex geometries, thinner, stiffer, larger, and so think about it. It's a consumer product with very short product life cycles, and so being able to try something, go to pilot production, and then do mass production within the space of weeks is a game changer. And so you can do things like pilot production with a shop system, and then mass production with the P50, the production system. This is an example of not a fully assembled build box, but just the 8-liter box you can have on the shop system start to make I think it's a few dozen at a time. And then you want to scale to thousands. So that's kind of on the enclosures, or at least in a few of the enclosures I can talk about. Next is a few examples of mechanical components and systems. And by the way, I see there's questions coming in. Awesome. We'll try to answer some along the way, and then we'll answer the others at the end. So the cool thing is you can now print entire subsystems. Here I'm showing examples from power drill, not necessarily an electronics component, but it's got electronics in it, and it's one we actually can show. But this is, you imagine if you have moving components, you have power transmission systems. These are all of the gears inside a consumer power drill. And so I'm going to show a few of these components. Normally, these would be metal injection molded. The precision is such that you can't, other methods aren't as great, and you need the cost to be obviously super low. And so this might be $500,000 or more in just tooling costs. Now imagine you're making a few flavors of this. You need different gearing systems, different parts of the world, different models. And then you want to make a few prototypes, go to pilot, and then do mass production. Well, with additive manufacturing, you can print literally thousands of these gears if you need to per day, or you can make just 10 or 20 gears, 10 or 20 sets. The beauty is, as the model changes, the cost of change is essentially free. There's no tooling cost. And so now entire subsystems, I showed this kind of cool example that at least I'm enamored with, but this is one part. This is one of the cool things of printing with 3D printing. You can print in place entire assemblies. As another example, not that this is an example of electronics, but just to give you a flavor. So here's chainmail printed as one piece. So now you can really do entire assemblies printed as one piece. So really consolidate assemblies, do part consolidation. All right, next. A few examples of thermal management. So I showed this heat exchanger already. So this is a custom one. Here's internal fins. Internally, there's cooling channels. Kind of show that in the part on the left. And here's the part printed in copper. Why copper? Maybe, maybe you need so much conductivity that aluminum at 200 watts per meter degree Kelvin is just not conductive enough, and you want 300, 350 watts per meter degree C, copper. Another great example, kind of an electronics component. So this is a heater body in a leading 3D printer. So it needed to heat air and some other parts, and so this is a custom part designed without tooling. Normally, it might be for this complex geometry. You could either do a much larger part and do machining on it. That becomes expensive. You could cast, but then the part would be larger and it would actually encroach into the build volume. Here, you have something that's no bigger than it needs to be, allowing for larger print volume. It doesn't use more material than it needs to, so it's lower cost. And since there's a moving part, it's less wear and tear on the motors, so that you're not wearing out the motors more than you otherwise would. So that's one example of a complex internal part. And by the way, this part went through a lot of iterations. So imagine if each one you're probably not going to cast them in low volume. And so machining, this would have been a nightmare, or at least our major engineering challenge if there wasn't a way to just say, okay, give me the shape I need and print it today. Show a few examples of electrical components. So this is an example, copper bus bar with different size holes for different wires. And there's actually so much, so this is a grounding way to do the ground. So one of the wires in the circuit would come here, and it gets so hot that there's actually an internal cooling channel. I don't have this cut in half, but I show the upper illustration hopefully shows you. So now you can print geometry that would otherwise be an impossible geometry to create, internal conformal cooling channel. This becomes a trivial thing with 3D printing. Custom connectors, of course, work in electronics, maybe power electronics. You need to bring a bunch of wires together. Maybe it's a bunch of wires plus light emitting diodes, other kind of components. So you want to mass produce these. Normally you might cast or metal injection mold them, but now you can just 3D print these parts. So that becomes trivial. This is kind of a fun project. There is a mansion in North Carolina that there's a giant kitchen island. And for that giant kitchen island, they wanted an overhead custom designed chandelier with a very specific aesthetic. And so there's all sorts of things involved here. There's quartz tubes, LED strips, there's pieces of machined aluminum billet, even carbon fiber involved. The goal was to power this entire installation without any visible wires. And the suspension parts would serve as the power connection, but there was needed to route the electrical path without doing it without any wires. And so the solution was essentially have a channel to connect a copper bus bar to provide the power. And so that custom copper bus bar was printed on the studio system. The challenges were, this is a relatively large, several inches, 8 or 10 inches, I think, part. Needed high dimensional accuracy, needed to be flat. You got high aspect ratios. It's kind of in the old days, this would have been this is a nightmare part to 3D print. It's got all the things you try to stay away from with the design rules. And there's some fine details. Bottom line is part was printed, sintered successfully, and assembled. Here's the bus bar mounted into the carbon fiber CNC plates, and here it is in various stages of assembly. And you can see on the right is the parts, the electrical system being testing and actually emitting all sorts of light. We will update this case study with here's what the actual chandelier looks like once it's installed. The guy's kind of a psycho in a good way, designing it. All right, and last but not least, I'd be remiss if I didn't mention, so far told you all about the end use parts you can create. So for, oh, you know what, I should have mentioned a few of these. You could do knobs, fun, you know, custom knobs for precision electronics. You can then, of course, finish them in a variety of ways. So, you know, you have user interface kind of, user interface. You can have different designs on the controls and finish them in a variety of ways. Let's see, I think I showed most of the parts. Okay. In addition to actually making the parts, you can make the tooling. You can print tooling. And so here's, for example, a test fixture where, due to the operations involved, you couldn't just have it be in plastic. And so a metal part was printed that holds the cell phone while some soldering and rework takes place. So here's a custom, this would have been, that test fixture would have been kind of a nightmare to machine. This would take up, you know, a good machinist could be a day. And because you have, for the manufacturing floor, you typically make relatively few of something, you can't leverage the mass production to, you know, techniques like casting or stamping. If you're going to make a tooling, it's probably your machinist that's going to create the tooling, tool maker. And so being able to just 3D print, be able to have the design freedom, geometric freedom to 3D print exactly what you need in metal is a big deal. Another example, of course, also end effectors, end of arm tooling for custom end effectors. So here's an example with a desktop metal fiber system. I know I told you about our metal, but we also do have a polymer printing capability, and with a carbon reinforced PEC, so polyether ketone. So it's a very high temperature, ESD compliant material. And so if you're handling, let's say, circuit boards and you're moving them, testing them, and you don't want to, you know, electrostatic field to build up and then potentially kill some of the circuits, you can now 3D print custom end effectors pretty easily. So if you have a manufacturing floor, you can print both metal parts and ESD compliant end effectors, jigs, fixtures, tooling. It's kind of an old application, but just for completeness, it's fair to mention it. The thing I'll say about finishing methods is your familiar finishing methods are entirely applicable. So whether it's mass finishing, like tumbling in giant or parts or giant vats, where, you know, a human can stand on this giant barrel, or if you want to do smaller kind of stuff, broad array of however you finish your metal parts today, all of that is entirely compatible because the parts being printed are the very alloys you're familiar with. So if you need 316L, that's what the composition is. You need 17.4 pH stainless, that's what the composition is, and so on. So whether you're doing polishing, buffing, media blasting, tumbling, etc., all of those techniques work. Just I'll say a couple words on electroplating. You know, there's a bunch of different reasons why you may want to electroplate, whether it's wear resistance. For electronics, it's often whether it's corrosion protection, could be aesthetics. You know, let's say you have a knob on a stereo system or something, or different kinds of, you know, on premium equipment, some you want to plate it with silver or nickel or gold. You can do that pretty easily. Customers have plated with gold, silver, chrome. I don't know if I have it. Anyway, we've done black nickel as well, so sometimes a nice black finish. And I'll show the gold, not because this is a webinar on luxury goods and gold, but because this is just a few examples of, you know, if our customers can gold plate, can achieve this with nice small parts, you can probably do a great job with you know, whether it's your cell phone case or other components. And so in summary, the key takeaway, I think, is that metal binder jetting is a game changer for the electronics field. You can now achieve previously impossible or complex, difficult to achieve designs. And in many cases, not all, but in many cases, it's a great alternative to casting, stampings, forging, machine, you know, the standard ways you mass produce parts. And really, this is the beauty and the flexibility is that this impacts every stage of the product lifecycle. You can do early development, you can do pilot runs, you can do mass production, and of course, you can make tooling to make these things possible. Helps with reduce the part cost, and really is a game changer in terms of inventory. You can really streamline the supply chain. You can print just what you need. You can print on demand. You can have a week's worth of inventory instead of 3 months. So this is, and you can print it where you need it. And so mass customization's a possibility. So it's operationally a game changer, and the products you're making can be better for the consumer. They can be cheaper for you to make. They can be higher quality parts. So this is an exciting time to be making electronic components. So with that, if any of this sounded remotely reasonable, we invite you to take a look at some of your parts, subsystems, your applications, whether it's the electromechanical portions, the electrical component portions, the frame, enclosure parts. Some of it would be cool to evaluate whether they might be a fit for additive manufacturing with metal. All right. So with that, I want to thank you for your time, and you can dive into some of the questions.
Yeah, so a couple of common themes in the questions. One, can you talk a little bit about the material properties, sort of hardness, heat resistance, strength, things like that for the parts?
Absolutely. So the good news is for all of these alloys, all of the alloys we're and our customers are printing, there are standards for not just the composition, but the material properties. So there's standards, and we work and tune both the powders, the entire process, so that they meet and exceed those standards. The short answer is everyone's welcome to, if you go to desktopmetal.com, go to the materials page, you can actually download the data sheets, and you can see, hey, what's the yield strength, etc. Yield strength, ductility, thermal conductivity, if you care about copper, that kind of stuff. The slightly longer answer is, if you think about, if the gold standard for material properties is wrought material, MIM-based processes can approach it, can come pretty close. Elastic modulus, for example, mechanical stiffness. Elastic modulus might be, that goes as square root of the density. If the density is 99, 98%, elastic modulus might be 95%. So if steel is 30 million PSI, this steel might be 29 million PSI. But things like yield strength, ultimate tensile strength, that might be within 10, 20% of wrought. And so there's kind of, there's standards. We stay above the standards, and the MIM kind of metallurgy allows you to approach wrought kind of qualities.
And specifically on hardness? Sorry,
hardness. I talk so long, I forget the second part. Hardness. So out of the furnace, first of all, it's alloy specific, but let's take 17.4 pH stainless steel. You might get 28, 30 Rockwell C scale hardness with some heat treatment, and all the heat treatment works just exactly the way you're familiar with. So you can use your existing H900 or some other process, the trade-offs between hold times and temperatures, etc. And so you can tune, but basically with heat treatment you can get the 17.4 up another 10, 12 Rockwell C points. So instead of 28, you might get to 35 or close to 40. There's also, you can do plasma nitriding. There's specialty things. You want to get to 60, 65 Rockwell C, you can do it. So there's, I guess it's not a short answer, but long answer is you can get into the 30, 40, or even 60 Rockwell C, and you can do even better with the tool steels, for example, 4140.
Great.
Let's see.
Another sort of set of questions sort of around, I guess, machine selection. So can you talk a little bit about the differences between studio, the shop production system, when you might want to use one versus the other?
Sure. If you want to make 1 or 3 parts today, you want to make a few parts this week, but you want to do it in your office, and really with minimal, human intervention, where you design the part, you send it to the printer, and then you move it from the printer to the furnace. So it's like 30 minutes total human intervention, and then you get your metal part. You want to make a few parts this week, studio system. You want to make a few dozen parts, 10, 20, 50 parts today, shop system. You want to make hundreds or thousands, then it's the production system. The trade-offs, on the one hand, the production system is all in, is more expensive than the shop system. On the other hand, its throughput is 20 times higher. You can amortize the cost much faster. And so if you need parts that are just a few cents, then your answer is production system. If you want to make a few, bespoke parts and a couple dollar kind of a price might be acceptable, then the shop system could be that way. So it really depends. It's a very easy thing to choose if you pick, and we can help you with this. Pick a few parts, kind of your small, medium, large parts. Let's look at the parts. Let's look at the quantities. It's very easy to tell from that what's the right system you need.
Another question on sort of part size, like, a lot of, obviously these are smaller examples. So sort of what's the optimal part size, how big, how small?
So what I don't recommend is the thing my colleague Jonah, who's leading the project, has done, which is print a giant manifold bigger than my head. Yes, it's a nice existence proof, but that's not the kind of parts you should be printing. I would say small. Everything that's MIMmed, small might be a golf ball size part. I mean, you can do much smaller. People have printed tiny hinges, little clips, custom clips for smartphones, where you can make literally thousands in one build, thousands or even tens of thousands in one build. Or here, I'll show this just for size. This is actually a part from the luxury webinar, but you see this ball. I know it's hard to see, it's not in focus, but give you a sense. That ball, it's actually geometry that's nearly impossible to cast because it's hollow. It's got a pattern on it. You can make many thousands of those at once. So you can make pretty small parts. How big? Well, to give you a sense, so parts that fit in your palm of your hand. So it could be kind of softball sized. I mean, this obviously is a part that's I don't know, it's my cell phone-ish. So the answer is kind of depends. But if it fits in the palm of your hand, it may be a pretty good candidate.
Great. And I think maybe the last sort of common thread we have is a little bit on materials. If you kind of break those down sort of by system and sort of what might be available.
Sure. Let me just, there was one question on the size. Somebody correctly pointed out, you show small parts. What about car manifolds and larger parts? The answer is of course, but this is electronics, kind of webinar. There's literally racing cars driving around with giant custom engine mounts that are probably 12 or more inches in build envelope. So large parts can be made. Custom manifolds can be made. Sorry, Nick, what was the other question?
Materials across systems and availability.
Yes. So there's the shop system. Shop system today, our customers are printing 17.4 pH steel. Several more materials, including tool steels, cobalt chrome, 316L. They're coming in the near future. The production system is actually an open system. So there's a range of materials that we have qualified, and some are being qualified by our customers. Since they're open systems, we might help you develop, but then you might decide, hey, I want to get the production system and do some development and do material development, and that's entirely possible as well. They're open systems meant to be printing everything, and eventually very highly reactive materials, aluminum, others, titanium's coming. So the production system as a platform is excellent for if you want to do really advanced kind of materials development. So steels are easy, Tool steels are coming. Aluminum is longer time frame, but probably on the order of a year or so. And a bunch of other, whether it's titanium or other specialty materials, they're coming. Fundamentally, the production system, it's not just an open system. It is engineered to be a system with which you can work with very highly reactive metals. And that's done. So it's an inert environment. There's a lot of steps taken so that you can take, this is one of the challenges with powder metallurgy, is you're dealing with powders, metal powders, and some of the metal powder is extremely reactive. And so it becomes a risk. And so a lot of work has gone into making it a very safe system for materials that otherwise there was no other way to work with them in powder form because of the dangers. Should I? Next questions, Nick, or should I go down this list here, or what do you think?
I think you can go down the list. Some specific ones in there based on applications. It's probably better to cover.
Sure.
One, but.
All right, I'll try some of these. Let's do a speed round. What are your headwinds? I'm assuming that means what are the challenges? This is a new technology. New technology, a lot of excitement, but new technology. We're advancing things quicker, and things are getting better. Our studio system is today, I would say it's bulletproof. There's a lot of advancements and improvements we've made just in the last year and a half on the studio system. The binder jetting systems, they're printing parts today, but these are still the early days. So it doesn't work for every application. You got to think through, this is a new area for us and our customers. And so we will learn together what are the new applications, what are the early applications that absolutely make sense, and which ones require some advanced development in terms of equipment and systems and binder and kind of process tuning. So I'm guessing 2 years from now, with these binder jetting systems, people will be making parts that are today quite difficult to make. So the headwinds it's not so much a headwind, it's just part of the fun and reality of early stage. These are the early days. So really it's just the leading manufacturers. There's a lot of them. I can tell you there's hundreds that are already using this and thousands that are exploring it. So it's there. But if you think about, there's 250,000 manufacturers worldwide. Binder jetting is they're just starting to wake up. So the headwind is just, technology adoption life cycle. All right, any application for printed circuit boards? Well, enclosures for printed circuit boards, of course. Is it just a binder being deposited in between layers of printed part? No. So the idea is this: a thin layer, maybe 25, 50, 100 microns of powder is spread. Then, just like as if that was a sheet of paper, imagine an inkjet printer spreading for that layer, spraying binder to decide what will be solid, what won't be. And then you go just like that. And so you have powder, and when you're ready to print the next part, you just need a little bit of powder without any binder in it. So that's enough. The powder is dense enough so that you can print part on top of part. And then later you depowder and remove all the extra powder. Is electromagnetic soft iron available for solenoid core, relay, and electromagnetic shielding applications? I'll answer 1/4 of that question. You can do electromagnetic shielding applications. I've seen some with these parts, but let's look at your specifics about is it with electromagnetic soft iron and the core relay kind of stuff. It's been a while been about 20 years since I designed something like that. All right, looks like a lot of waste in the studio with a very large brims. Why is that? Yeah, the studio is not a way to make high volume, cost effective parts. What you saw was, and by the way, that was a very high aspect ratio part. There was a very long bus bar, and we want it to print on a flat, print and center on a large flat plate. Most parts, so for example, here's a heat sink I didn't show. Here's the platform it gets printed on. The support is essentially a little plate that's the size of the part. Not a lot of waste here. Most of the part is the heat sink itself. So really it's part specific. That was an extreme case. Test fixtures was printed with the FFF system. Yes, the cell phone test fixture was printed because you need just a few of them. So that was printed with a studio system. Do we have experience with FDA and medical? Their material certificates on the materials. We have customers printing medical applications, including there's a variety, everything from ventilators to surgical devices. It's not yet implants, not yet. That's coming. And my understanding is the FDA certification takes place at the part level, and so once the part is printed, the manufacturer can take steps towards that. We do have both plans, and it's part of our workflow to qualify materials for use for these applications. I'm just going to go. What is different in the production system that makes it open? So it's not that we locked down the shop to make it closed. It's more that what we saw was a need by a lot of machine shops and kind of contract manufacturers that want a turnkey system where there's intentionally not a lot of knobs to turn. There's still some, but not a lot. Versus, in some cases, for the production system, if you have more knobs to turn, you can make better parts. And so both the production system, the P50, as well as the P1, which is it's like a mini-me version of the production system. It's a development platform. It's a bridge to production. Same open system, but just a much smaller build volume, so you can do a build in an hour, and then, for development purposes. So just a lot more of the there's inerting. If you go to the production system page on the website, you'll see a lot of the technologies. The single pass jetting. It's really engineered. Everything about it is engineered for mass throughput, and so part of and it's not that open is the only characteristic. There's a ton of stuff in there about working with inert parts, about making hot swappable modules that are very easy to service. So open is just, if you're going to make a system like that, you're selling it to a sophisticated organization, and so they're capable and not just open to, but prefer a system where a lot of the process knobs can also be adjusted. What about ceramics? Give it some time. I'm not saying no, but I'm also not launching a ceramics product right now. But it's not an unreasonable thing to think that these systems will be binder jetting, not just metal. Do you need to cure the green parts? The answer is yes for the binder jetting application. And really, it's the green parts come out. Now, you can already work with them quite nicely, but if they go into an oven for a little bit to dry, and it's 160 degrees C for a little bit, or 160 degree max, it makes them really super solid. So you can, for example, when you're depowdering, even very thin, long parts, you can work and imagine drills, or imagine these pens. You can handle the parts very, without kid gloves, and you can depowder them with great yield. Someone said, I have the shop system already, want to try different materials. Would that be possible? Talk to us. If you'd like, we can help you maybe beta test some of the new materials coming. All right. If we could sample pieces, do you have electroplating capabilities? Do we need to go to a third party for plating? One way or another, it's pretty straightforward to plate parts. Our headquarters is in Burlington, Massachusetts. I've used a plater for the last 25 years. That's 7 minutes away. So you got to be careful about what's the process. Do they have certification and process controls? But it's basically trivial. All of these we've done, or our customers have done. You do a nickel strike on the steel just for adhesion, and then put anything over it you want, whether it's copper plating, nickel, chrome, black nickel, gold, silver plating, etc. All right, I think that's. More questions. What's the density you've achieved through the shop production systems? It's greater than 99%. So we're shooting for even higher, but in practice, and by the way, that the voids are very fine voids, like 5 to 15 microns in size, and they're very nicely dispersed. In other words, you can have parts that can take pressure, it can take vacuum. There's not a continuous path through the voids, and so you get great material properties, and you can do vacuum testing, leak testing. All right, we'll maybe keep it going for another 5 seconds. See if there's any other questions. Otherwise, I want to thank everyone for your time, and we'd love to talk to you about your applications. All right, have an awesome day, everybody.